Static electricity is everywhere, from balloons to lightning storms to giving yourself a shock by touching a door handle. This common phenomenon has been studied since the time of the ancient Greeks, so you might be surprised to learn that scientists don't know that much about how static electricity actually works.
I would say we know virtually nothing. Some people will get mad at me for saying that if they watch this video. I think we know some things about particular situations, but kind of the overall picture of what happens most of the time for most materials, we don't know much.
The basic idea is that static electricity is an imbalance of charges that occurs when charged ions or electrons move from one object to another. This kind of charge transfer is often called the triboelectric effect, or tribocharging, and it's caused by two surfaces rubbing against each other, or even just coming into contact.
Whenever any two objects touch, they exchange charge. It's literally unavoidable. So right now sitting in my chair, I'm moving around, I'm exchanging charge with the chair.
So we know it happens, but we don't really know why.
For example, if I give you rabbit's fur and a balloon, and I rub the balloon on the rabbit's fur, I can't even tell you what is different about the rabbit's fur and the balloon that makes them exchange charge. Could it be their electronic structure, chemicals on the surface, their thermoelectric properties, flexoelectricity? So I literally can't even tell you what is the driving parameter.
And if we don't understand what's driving static charge, then we don't really understand what causes lightning in thunderclouds or volcanoes, or what makes little bits of rock dust come together around a star to form planets, or how to avoid getting electric shocks off door handles.
Industries care a lot about static electricity, mostly because they're trying to avoid sparks. A classic example that's maybe a bit older now is a coal mine explosion. But even in high-tech settings, for example, in a clean room, where they make computer chips. These are environments where you have to have everything extremely free of airborne particles, because if that particle lands on your computer chip while you're making it, it will mess everything up. And the reason those particles attach is because of static electricity.
Scott's one of a relatively small group of researchers trying to understand this at the fundamental level, which is easier said than done.
And it's actually a really hard problem because, when you rub two things together and they get really charged, it seems like, oh wow, they're really charged, my hair's sticking to the balloon, it's so big. But actually, maybe 1 in 100,000 surface atoms gained or received a charge. And so when you're trying to do any kind of technique to see what that 1 in 100,000 was, it's a lot like looking for a needle in a haystack.
So the team set out on a needle hunt, and they started with an even more intriguing puzzle than balloons and hair. Why does charge still move from one object to another when they're both made of the same thing?
Let's say you have a grain and you have another grain and they're both made of exactly the same material. And if you contact them and you measure the charge, maybe this one will be a bit positive and this one will be a bit negative. And the question we wanted to answer is, what's the difference?
Gallia and Scott wanted to find the difference between two apparently identical objects. They were working with silicon dioxide, the compound in quartz and a big component of sand, and their approach to experimentation was to simplify things as much as possible. Take two objects, in this case a grain and a flat plate made of the same silicon dioxide, hit them together, then see how the charge has changed. And do this over and over again in different controlled conditions. Setting up the experiment was tricky.
You cannot touch the grains in any way, because if you touch them, you're going to give them some charge, and that's going to be more charge than they gained through the collision. So what we needed to do is isolate the grains. So we trap them in an ultrasonic standing wave. You turn off briefly the acoustic field, you let the grain fall on a plate, bounce, and then you capture it again.
After each collision, they measured the charge. Half the grains became more positive, half negative, seemingly at random. But the same grain always went in the same direction, either positive or negative. Clearly there must be some invisible difference that determines which way it goes.
Things that people have named as being important in tribocharging include humidity, roughness, surface chemistry, pH, mechanical properties, strain, electron structure, Z potential, phase electric constant, Z coefficient, dielectric constant, hydrophilicity, etc., etc. And you can probably find a scientist that will tell you that any of those is the most important one.
So the team started testing theories, trying to find the thing that makes the difference. And finally, they landed on something that did seem to make a difference. It was baking.
If you take the positively charging particle and you bake it, even at relatively low temperatures, like below 100 degrees. And you do the measurement again, it's going to charge more negatively.
Baking the grains was the key. And it turns out that the magic ingredient in this cooking process was carbon. All around you are tiny little carbon compounds that float through the air and land on everything. It's often just a few molecules, but this stuff is absolutely everywhere. And experiments showed that baking got rid of the carbon compounds, cleaning the surface of the oxide grains. This made each grain charge more negatively than it did before, until the carbon started slowly landing on the surface again and the effect wore off. So could bits of carbon explain the invisible differences between otherwise identical samples?
What exactly goes on the surface is a little bit random. It depends a little bit on whatever molecules were in the air at the time. And so this tells you that if you take two really clean samples and you store them in a box for a few days, they're going to end up slightly different. And this slight difference explains why certain samples want to charge positive and others want to charge negative.
Finally, there was a clear signal, a variable that actually impacted the static charging of these little oxide grains. But is this really the answer to the centuries-old puzzle of static electricity? Are carbon compounds the one thing that always makes the difference?
So we're very cautious just because this is such a messy topic. That I personally have learned my lesson not to say that, the thing we saw here matters everywhere. So I would not be surprised at all if these molecules from the environment matter for other materials. But until we get a big body of experimental evidence, I'm not going to stick my neck out.
It could be that surface carbon only matters for the oxides which they tested in this particular experiment. Different materials could have different key factors. But knowing how it works in oxides is pretty useful.
They're actually one of the most common materials in nature. So something like 60% of the Earth's crust is made from silicon dioxide. And the same is true for most other terrestrial planets. So recently it was discovered that there's lightning on Mars. And that was because of the oxide particles on Mars colliding, getting charged up, and then somehow getting separated to create, lightning and dust storms.
Whether the lightning is on another planet or in the clouds pouring from an active volcano, it all comes down to tiny static interactions between grains.
If you look at a system, for example, like volcanic lightning, you have these silicate particles that are thrown very violently in the air, and the temperature changes, the pressure, humidity, there's all of these complicated things happening. But if you don't understand just a little microscopic mechanism, just what's happening when particle A and particle B collide, then how can you explain the big picture, right? And there are so many little open questions that maybe you could answer by just understanding fundamentally what's happening at the scale of the particles.